Oh, this is a weird gadget. It's a device that is designed to take your phone and then it rocks your phone to give the illusion that you're walking. And the only reason I can think they could use this, I mean, it translates basically to home pedestrian. And the only reason I can think of this is to give the illusion that you're walking long distances in an app that records that. I don't know why people would do this unless they're put on forced health regimes. But I'm plugging it in. I'm going to start it rocking. And as you can see, it just keeps rocking. You can hear the slight bump as the magnet gives it a kick. So it comes with a rubber band, and you stick your phone in like this, and the rubber band goes round the phone to hold it in place. It's quite nice. It's got little bearings here for the rocking mechanism. And you put the rubber band round, and then you stick it in to the frame, noting that the plastic legs had to be pulled out slightly to fit, and then it rocks the phone. Lovely. Okie dokie. Right, let's take it apart and see what's inside. It can also accommodate two phones. Why? Is this so that two people can exercise at once, or is that a different size base? Not sure. It feels quite heavy. We'll open the base up as well. I can already see there is quite a chunky magnet here. It is not battery operated, but apparently, going with the instructions, there are versions that you can tell it you want to walk for a certain length of time and then stop walking and it will turn itself off. And I presume that's so you don't fall asleep in front of your TV and then accidentally walk 300 miles. I can imagine your health advisor saying, well done, you've walked 300 miles this week, but unfortunately you've still gained 4 pounds. I'm expecting a slab of steel in here because it is heavy. You'd think the phone... Oh, it's ball bearings. Ball bearings have been rammed in to give it extra weight. Okay, let's open this. Now, I'm guessing there may be screws under these feet because this thing was held together with screws. Might not be screws. No, there are no screws. Okay, right. Spudger time it is. This thing will be clipped together. I can think it would be quite nice. It wasn't that expensive. It would be quite nice, the base. I think this might have been from AliExpress. If it was, I shall provide a link to that, just in case you want a magnetic swinger. Particularly a USB-powered one. Now, how is this going to come out? Is it glued shut? I hope it's not glued shut. No, it's not. It's not glued shut. I can see it trying to part the Moses effect. I'm going to have to try and force this apart. It's one of these well-designed cases that clips together super tightly. This is where I found there were, in fact, screws. Oh, yeah, this isn't going well. That's okay. Sometimes it doesn't go well. It may be the push-in pillar version. That looks promising. What do we have? What do we have inside? Is it this single transistor pendulum system? What is this clipped into? Are things just breaking? They might just be breaking. I'm not sure. It's the single transistor system. Right, tell you what, I shall draw this out. Let's zoom on this so you can see. And zoom up. Is that in focus? Yes. It's a little transistor and it's a 3-terminal coil. So I shall desolder that and I'll measure the impedance of... It's a very small coil. That's quite good. The other ones usually have very big coils. Okay, I shall reverse engineer this and I'll desolder the coil and I'll measure the resistance to the windings. 1 moment, please. Okay, let's explore. Very simple circuit, but also very clever. And this circuit goes back to the dawn of electronic clocks, when the first pendulum electric clocks that used a transistor were designed. They used virtually the identical circuit to this. So we have a transistor here, and we have 2 windings with a sender tap. I was fooled at first by the diameter of the windings. I tried measuring them. I didn't realise you can't even see. It looks as though I'm holding nothing here. But what I'm holding here is the thin wire that is the feedback winding, and oddly, for the last, let's say the last about 4 inches or 100 millimetre, they've twisted multiple strands of the same wire onto that just to give a stronger end so they could wrap it round the pillar without it snapping. Because I found when I removed this bit, and when I tried wrapping the original around the pillar, it just kept snapping because it is so super thin. You can see the light reflecting off it, but it is ultra thin. So that's this winding here, and it's 0.05 millimetre. There are lots of turns of that. I didn't unwind it because there's 2.7 thousand ohms, so that's going to be an awful lot of turns. The other winding is much simpler. It's only about 31 ohms, much larger diameter cable, and I've noted the cable diameters down on the schematic. And then there's a transistor, and I'll show you the schematic. It's the best way to describe how this works. Here is the schematic. Other things worth noting before I show you that. Here's the coil. It's not a very big coil compared to the traditional pendulum kickers, but it has a steel core that is inserted up the middle and held in place by a little single-sided foam pad just stuck over the end. Right, let's zoom down on this Kundo electronic clock. That's what it used. So there is a representation of the end of that superfine wire, with the thin strand coming and then the multiple strands wound onto it. We have the USB power supply giving the plus 5 volt rail and the 0 volt rail. We have the transistor, and we have the kicker coil, and we have the sense coil. When initially powered up, there is no current flow because the base is effectively pulled to the 0 volt rail by the two windings. It's also worth mentioning that it's unusual to see an NPN transistor switching up to the positive rail, but it's viable in this application because it effectively has its own base current generator in the sense coil. So what happens is when a magnet swings by, it induces electrical current if it's the correct polarity magnet. That can be either as it approaches or leaves. The ideal situation is if the magnet's approaching, so it gives it a kick as it passes. But it induces enough current in this coil to actually create a voltage of above 0.6 volts on this transistor. It will basically be a point the transistor's just turning on. When the transistor starts turning on, it energizes this coil, and that gives a magnetic pulse to the core. But in the process of doing that, it also couples onto the feedback winding that was originally picking up the swinging magnet. And that means that because this is inducing directly onto that, it gives a very high current pulse, and it drives the transistor on hard, and current flows through this until it saturates the magnetic core effectively. It can't take any more magnetic field and therefore can't couple current across to this coil anymore. Once that happens, the drive to the base of the transistor starts reducing, the transistor starts turning off, the field starts collapsing, and then because this is now effectively seeing a negative voltage, it turns the transistor off solidly and it resets the circuit ready for the next swing. I've looked at these in the past, and I did find that when it turns off, and it does so very decisively, there was quite a high voltage spike across the winding, the collapsing, which the transistor is not actually protected against. I wonder if you could actually put a diode across that. I wonder if that would adversely affect it. Because it's building up magnetic field, then it's collapsing. That would effectively shunt that, but it would also kind of reduce the negative drive to the transistor. But this is the simplest circuit. You see these in the kinetic pendulum ornaments, or they used to call them perpetual motion ornaments in the past because they ran so long from a battery, because it's a fairly small current pulse, and it's just brief spikes just to magnetize the core just each time the magnet passes. Sometimes you do hear them buzz though as they pass, so it may be actually firing multiple pulses. Other versions of the circuit do have a damping resistor and capacitor to maybe perhaps control that, just so it's a single pulse. But there we have it, the exercise system for big people who don't want to exercise, and this thing could possibly have other uses. It's quite nice. It's got these little bearings, I've mentioned that before, and to make sure it rocks absolutely freely. But quite interesting as a little pendulum system. Quite a nice and novel thing. Quite neat to take apart.